Section. Introduction. Let's start with a brief introduction. In the world of machine vision systems, a common approach is to use a feature extractor network, often referred to as a backbone. This backbone can produce a variety of outputs, such as a dense array of features for object detection and localization, or a single feature vector for classification or image retrieval. While it's possible to train these backbones from scratch using task-specific data, a popular method is to use pre-existing backbones that have been trained on large benchmark datasets and then fine-tune them for the specific task at hand. This method, known as transfer learning, has several benefits. It can significantly reduce the amount of data needed for deep learning applications, speed up training, reduce computational costs, and improve performance across a wide range of applications. Additionally, because the pre-training datasets often contain images from a variety of domains, the resulting models are robust and can be applied to a variety of tasks. In the early days of deep learning-based vision systems, ImageNet pre-training was heavily relied upon. However, today, there are many different pre-trained models to choose from, each with its own strengths and weaknesses. The performance of these models can be influenced by three main factors: the architecture of the model, the pre-training algorithm used, and the dataset used for pre-training. With so many options available, it can be overwhelming for practitioners to choose the right model for their computer vision system. To help practitioners navigate this complex landscape, we've conducted a comprehensive comparison of many popular pre-trained models, which we've dubbed the Battle of the Backbones, BOB. In this comparison, we've evaluated these models on a variety of tasks, including image classification, object detection and segmentation, out-of-distribution generalization, and image retrieval. Our goal with this benchmark is not only to assist practitioners in building computer vision systems, but also to guide the research community towards promising areas of research in the quest to design better backbones. Through this comparison, we've been able to identify the strengths and weaknesses of different pre-training routines and architectures, debunk popular misconceptions, identify fundamental limitations, and highlight promising areas for improvement. Here's a quick summary of our findings. In our comprehensive evaluations, the top-performing models were the supervised convex base, supervised SWIN v2 base trained using ImageNet 21K, and Clip Vit base. Among smaller backbones, convex tiny and SWIN v2 tiny performed the best, followed by Dino Vit small. Despite the recent focus on transformer-based architectures and self-supervised learning, we found that high-performance convolutional networks pre-trained via supervised learning outperform transformers on most tasks. The superior performance of supervised pre-training is largely due to the availability of larger training datasets. When comparing models trained on the same scale dataset, self-supervised learning (SSL) models outperformed their supervised counterparts. Vision transformers, VITs, were found to be more sensitive to the amount of pre-training data and the number of parameters than convolutional neural networks, CNNs. We found a strong correlation between performance across tasks. The top-performing backbones tended to perform well across all tasks and settings. Before the rise of SSL and vision language modeling, most backbones were pre-trained on ImageNet. However, since 2020, methods like SimCLR and CLIP have popularized these areas and sparked a lot of new research. While there have been previous benchmarks comparing large collections of backbones on diverse tasks, the rapid progress in pre-training algorithms, training sets, and architectures means that this area deserves renewed attention. Section Summary. The dominant approach in building machine vision systems involves using a feature extractor network, backbone, that is pre-trained on large benchmark datasets and then fine-tuned for the specific task. This transfer learning approach reduces data requirements, speeds up training, and improves model robustness. In a benchmark called Battle of the Backbones, BOB, supervised convex base, supervised SWIN v2 base, and Clip Vit base performed the best across various tasks, datasets, and settings. Despite the recent popularity of transformer-based architectures and self-supervised learning, convolutional networks pre-trained via supervised learning outperform transformers on most tasks. Section. A Guide to BOB. Let's delve into the world of BOB, or Battle of the Backbones. This is a comparison of various backbone models, each with its own unique architecture, pre-training routines, and datasets used for pre-training. We've compiled a comprehensive overview of these backbones, including their pre-training algorithms, datasets, and architectures. For more detailed information, you can refer to the appendix section titled Backbone_Details. Now, let's talk about scale and the importance of a fair comparison. Many of us have limited computational resources and need to adjust hyperparameters on our own datasets without exceeding our budget. To mimic this situation, we've conducted moderate hyperparameter sweeps, avoided excessively long training schedules, and excluded architectures larger than convex base, with the exception of the stable diffusion backbone, which doesn't come in a smaller size. We've also only used publicly available checkpoints that would be accessible to anyone. However, due to the varying amounts of hyperparameter tuning and different pre-training algorithms used on different datasets and architectures, a precise comparison isn't feasible. Despite this, we believe this comparison is relevant for practitioners as it reflects realistic conditions. Next, let's discuss the tasks we use to evaluate the backbones. We've divided these tasks into 4 categories. 1. Classification. We assess the performance of the backbones on various classification tasks, such as identifying natural, medical, or satellite images. This requires the backbone to extract features that identify the content of an image's foreground. 2. Object detection and segmentation. Unlike image classification, these tasks require backbones to extract features that pinpoint the exact locations of objects, either on a pixel basis for segmentation or with enough detail to draw bounding boxes for object detection. 3. Out-of-distribution generalization. In real-world applications, computer vision systems often encounter data that doesn't match their training set distribution. We evaluated the model's ability to generalize to new downstream domains. 4. Image retrieval. This task requires a backbone to match similar images based on proximity in feature space. We explored tasks that require matching images based on various criteria such as semantic content and visual similarity. For each task, we've detailed our experimental setup, including learning protocols, datasets, and evaluation metrics. We've also provided complete experimental and implementation details in the appendix section titled Experimental_Details. In the classification task, we evaluated pre-trained backbones on various datasets using 2 fine-tuning protocols: end-to-end fine-tuning and linear probing. We conducted experiments on 6 common image classification datasets, covering multiple domains such as natural images, satellite images, and medical X-ray data. We evaluated the models by measuring classification accuracy and area under the ROC curve, AUC, on the test split. We also benchmarked the latency and memory usage of each backbone on the same device. For object detection and segmentation tasks, we used the Cascade Mask RCNN framework and conducted experiments with 3 protocols: end-to-end training from random initialization, end-to-end fine-tuning using pre-trained backbones, and fine-tuning with frozen backbones. We conducted evaluations on the popular COCO dataset and followed the COCO-style average precision (AP) metric. Section Summary. The section provides an overview of the backbones used in the study, including their architectures, pre-training routines, and datasets. It also discusses the limitations of comparing different checkpoints due to variations in hyperparameter tuning, pre-training algorithms, and datasets. The study evaluates the performance of the backbones on various downstream tasks such as classification, object detection, segmentation, out-of-distribution generalization, and image retrieval, using different learning protocols, datasets, and evaluation metrics. Section: Out-of-distribution generalization. We're going to discuss a concept known as out-of-distribution generalization. Modern networks are typically trained on specific data distributions and perform well on them. However, when these models encounter data that deviates from their training distribution, their performance can drop significantly. We're interested in how well these models, or backbones, perform on a variety of tasks, and how this performance holds up when they're faced with data that's outside their training distribution. To evaluate this, we use several datasets and benchmarks that have been designed to test a model's robustness when it encounters data that's different from what it was trained on. Specifically, we're looking at how well the models generalize on 2 tasks: image classification and object detection. We're also interested in 2 types of distribution shifts: variations in structure and style within ImageNet, and the transition from synthetic to real-world data. We use several benchmarks to evaluate out-of-distribution performance. For changes in structure and style, we use 4 different ImageNet datasets: ImageNet A, which contains challenging test images; ImageNet V2, a test set of images similar to those in the original ImageNet; ImageNet R, which contains artistic renditions of ImageNet categories, and ImageNet S, a collection of black and white sketch images from ImageNet categories. We also evaluate how well models trained on synthetic data perform on real data. Synthetic data is often used when it's difficult or costly to gather real-world data. We use two benchmarks for this: VisDA Syn to Real, which contains synthetic and real images of objects from 12 classes, and Sim10K to Cityscapes, which uses synthetic Street View images for training and real-world Street View images for evaluation. We measure performance using classification accuracy for image classification and mean average precision for object detection. We also conduct evaluations on a variety of image retrieval datasets. These include the Oxford and Paris datasets for geographic landmark retrieval, the INSTRE dataset for object retrieval, the Caltech UCSD BIRDS 200 dataset for fine-grained retrieval, the iNaturalist dataset for natural images, the ObjectNet dataset for real-world scenarios, the Google Landmarks V2 dataset for large-scale landmark recognition, and the INRIA CopyDays dataset for holiday photos. We categorize iNaturalist, ObjectNet, and Cub 200 as semantic retrieval datasets, while the others are considered content-based retrieval datasets. We measure model performance using mean average precision, recall at K, which measures the proportion of correct matches among the top K, and mean reciprocal rank, which calculates the average of the reciprocal of the number of results returned before the first correct match. For all these metrics, higher scores indicate better performance. Section Summary. The section discusses the importance of evaluating the generalization of trained models on out-of-distribution (OOD) settings. It introduces various datasets and benchmarks used to evaluate the robustness of models to distribution shifts, including structure and style variations within ImageNet and synthetic to real generalization. The evaluation is conducted on tasks such as image classification, object detection, and image retrieval, using metrics such as classification accuracy, mean average precision, MAP, recall at K, and mean reciprocal rank, MRR. Section. I'm a practitioner. Which backbone should I choose? As professionals in the field, we often face the challenge of choosing the most suitable backbone from a vast array of options, each with different sizes, training methods, and pre-training data. So, how do we decide which one to use for a specific task or in general? In our study, Bob, we systematically compared publicly available backbones across various tasks, datasets, and settings. We used a ranking protocol to make these comparisons. Firstly, we calculated the z-scores for each backbone in a specific setting, such as top 1 classification accuracy on ImageNet. The z-score is a statistical measurement that describes a value's relationship to the mean of a group of values. It is calculated by subtracting the mean from each value and then dividing by the standard deviation. This gives us an idea of how well a specific backbone performs compared to the average performance of all backbones in that setting. Secondly, we compared backbones across different tasks and settings by aggregating and comparing the previously calculated z-scores. This gave us a rough ranking of the backbones. Using these rankings, we were able to identify not only the best performing backbones for each task but also the best backbone in terms of overall performance across tasks, datasets, and settings. For classification tasks, we found that the supervised SWIN v2 base trained on Indiana 21K, fine-tuned on Indiana 1K, performed the best, followed by ClipVit base and supervised Convenex base trained on Indiana 21K. For object detection and instance segmentation, the supervised Convenex base trained on IN21K was the top performer, followed by supervised SWIN v2 base trained on Indiana 21K, fine-tuned on Indiana 1K, and supervised Convenex base trained on Indiana 1K. In the case of image retrieval, the supervised Convenex base trained on Indiana 21K was the best choice, with supervised SWIN v2 base trained on Indiana 21K, fine-tuned on Indiana 1K, and ClipVit B trained on LAION2B, coming in second and third. For out-of-distribution, OOD, classification, we found that supervised Convenex base trained on Indiana 21K was the best, followed by supervised SWIN v2b trained on Indiana 21K, fine-tuned on Indiana 1K, and ClipVit base trained on LAION2B. For Synta real object detection, the supervised Convenex base trained on Indiana 1K was the best backbone, followed by supervised Convenex Tiny trained on Indiana 1K, and supervised convex-based trained on Indiana 21K. For those with no specific task in mind, the best performing models in terms of aggregate performance were supervised convex-based trained on Indiana 21K, supervised SWIN V2-based trained on Indiana 21K, fine-tuned on Indiana 1K, and clip-vit-based trained on LAION2B. We noted that backbones trained in a supervised manner, SWIN V2 base, convex base, or with vision and language supervision, clip-vit base, outperformed the rest. For applications that require efficient backbones for faster on-device inference, we benchmarked 3 small backbones, REGNET-X400F, EfficientNet B0, and RESNET18, all pre-trained in a supervised fashion on ImageNet-1K. We found that EfficientNet B0 performed best overall and across classification, retrieval, and OOD classification, followed by RegNet X400MF and then RESNET18. Interestingly, ResNet still outperformed newer efficient architectures for detection and segmentation. Section Summary. In this section, the authors discuss the process of selecting a backbone for computer vision tasks. They compare publicly available backbones using a ranking protocol that includes setting-specific z-scores and cross-setting comparisons. For classification, the best performing backbone is supervised SWIN V2 base trained on Indiana 21K, fine-tuned on Indiana 1K, while for object detection and segmentation, supervised convex base trained on IN21K is the top choice. For image retrieval, supervised convex base trained on Indiana 21K is recommended. Overall, supervised convex base trained on Indiana 21K is the best performing backbone, followed by supervised SWIN V2 base trained on Indiana 21K, fine-tuned on Indiana 1K, and clip-vit base trained on LAION2B. For efficient backbones, EfficientNet B0 performs the best, followed by RegNet X400MF and RESNET18. Section: Observations and Trends. Let's delve into the observations and trends we've noticed in our study. Firstly, we compared the performance of vision transformers, VITs, and convolutional neural networks, CNNs. We found that modern architectures significantly outperform basic VITs. The best performing model was convex base, a convolutional model, closely followed by SWIN V2 base, a hierarchical transformer. This suggests that we should move beyond basic VITs, which are still commonly used. However, we didn't evaluate very large models, so it's possible that VITs might perform better than their advanced versions or CNNs at larger scales. Secondly, we found that VITs benefit more from scaling up than CNNs. We observed that the performance of both CNNs and VITs increases with the number of parameters, but this effect is stronger for VITs. Similarly, while the performance of both types of models increases with the size of the pre-training data, the correlation is significantly higher for VITs. This suggests that using larger models might yield different results, possibly favoring transformer-based architectures. Next, we looked at whether supervised learning or self-supervised learning, SSL, is better. We found that models trained with supervised learning generally perform better, but this is mainly because they are pre-trained on larger datasets. When we compared models pre-trained on similarly sized datasets, SSL or vision language pre-training methods performed better on classification and retrieval tasks, which heavily rely on the learned representations. However, supervised learning models still had a clear advantage for detection and segmentation tasks. We also found that performance across different tasks is highly correlated. This supports the current trend of using general-purpose foundation models for computer vision. However, the correlation was lower for the retrieval task, which could be due to the limitations of the Midas and May pre-trained models in this context. We also found that VITs benefit significantly more from end-to-end fine-tuning compared to CNNs, both for supervised and self-supervised pre-training. In terms of vision language modeling, clip pre-training performed the best among the basic vision transformers, even compared to models trained with supervised learning on ImageNet 21K. This suggests that we should consider more advanced architectures when conducting self- or weakly supervised learning. In contrast, models trained with a generative objective, such as May or Stable Diffusion, performed worse. However, we recommend caution when interpreting this result, as the evaluation of Stable Diffusion is currently limited to select tasks. When we compared smaller models, we found that supervised convolutional trained on in 1K performed the best, followed by supervised SWIN v2T trained on in 1K and Dino Vit-S trained on Indiana 1K. In terms of performance versus speed, we found a strong negative correlation. This means that larger models tend to perform better, but they are also slower. We also found that depth estimation may serve as a powerful and generalizable pre-training task for foundation models. In terms of calibration and test likelihood, we found that test likelihood is strongly correlated with accuracy, while calibration error has a weaker correlation. Finally, we found that CNNs and models trained with SSL are more robust to adversarial attacks. In particular, convolutional is more robust even when trained with supervised learning. Section Summary. The performance comparison between vision transformers, VITs, and convolutional neural networks, CNNs, shows that modern architectures, particularly convolutional backbones like convolutional base and hierarchical transformers like SWIN v2 base, outperform vanilla VITs. VITs benefit more from scale than CNNs, indicating that benchmarking larger backbones might yield different winners, possibly with transformer-based architectures. Supervised learning backbones dominate due to the availability of pre-trained models on larger datasets, but SSL backbones can outperform them with similar-sized pre-training datasets. Performance across tasks is highly correlated, supporting the trend of general-purpose foundation models for computer vision. Transformers excel under end-to-end fine-tuning, while CNNs excel under linear probing. CLIP pre-training, which combines vision and language, outperforms vanilla VITs and even ImageNet 21K supervised trained backbones, suggesting the promise of advanced architectures in vision language modeling. Backbones trained with generative objectives have inferior performance compared to supervised or self-supervised approaches. In the small backbone subset, supervised convolutional trained on in 1K performs the best. There is a negative correlation between throughput and performance, indicating that larger models tend to have better performance at the cost of speed. Monocular depth estimation shows competitive performance across various tasks, suggesting it as a powerful pre-training strategy. Calibration and test likelihood are correlated with accuracy, with self-supervised pre-training leading to inferior calibration. CNNs and SSL methods are more adversarially robust than VITs, with convolutional being the most robust even when trained in a supervised fashion. Section. Where are things going from here? What's next in the field? The backbone is the heart of every computer vision model. In our comprehensive comparison, we analyzed over 1,500 training runs to provide valuable insights for those working in computer vision. We evaluated the performance of various publicly available vision backbones across a wide array of tasks, including segmentation, detection, classification, and retrieval. We discovered that supervised conv-next, supervised SWIN v2, and CLIP models performed well across these diverse tasks. For settings with computational limitations, smaller versions of these architectures, namely supervised conv-next and SWIN v2, along with Dino with a small VIT, showed promising results. Our Battle of the Backbones, BOB, provides a helpful guide for practitioners to choose the most suitable backbone from a vast array of options. Looking towards the future, we noticed several significant trends. Firstly, we found that performance across different tasks is strongly linked, indicating a move towards universal backbones that perform well across various tasks, rather than specialized ones. Secondly, we observed that there is an inverse relationship between throughput and performance, suggesting that scaling could be a promising way to enhance backbones. Lastly, while our practical recommendations include many supervised models, self-supervised learning shows potential when compared to standard supervised training. By sharing all our experimental results and the code to test new backbones, we hope BOB will be a useful resource for both current practitioners and future researchers. However, it's important to note that the insights from BOB are based on the tasks, backbones, and settings considered in this study. We aim to provide practical insights for computer vision researchers, but these insights need to evolve as more backbones are introduced and more tasks and settings are considered. Our study primarily focuses on performance-related aspects, and there are other important factors, such as biases in models, that need further exploration. Our benchmark does not include backbones larger than conv-next base, except for stable diffusion, and the rankings may change at a larger scale. For example, while modern convolutional architectures pre-trained via supervised learning perform best on most tasks, we found that transformers benefit more from scale, both in terms of pre-training data and architecture size. Therefore, transformer backbones might outperform convolutional backbones at very large scales. Regarding the computation cost and carbon footprint, our experiments consumed a total of 127,000 GPU hours on NVIDIA RTX A100 cards. Assuming an average carbon efficiency of 0.37 kilograms of CO2 equivalent per kilowatt hour, the total emissions are estimated to be around 11,792.36 kilograms of CO2 equivalent. We would like to acknowledge the support we received for this work. MG and AGW were supported in part by NSF Career IIS 2,145,402, NSF IDISRE 1 NIHR 01DA048764001A1, NSF IIS 1,910,266, Big Hat Biosciences, Capital One, and an Amazon Research Award. HS and RC were supported in part by the ONR Murray Grant N0014-201-2787. VP, PC, and JH were supported in part by ARL, NASA ULI, Google, and NSF number 2,144,194. RN, MS, GS, and TG were supported by the ONR Murray Program, the Office of Naval Research, N000142112557, the AFOSR Murray Program, and the National Science Foundation, IIS 2,212,102 and 2229885.